This is my DIY thrust test stand. I made an intro video about this a few months ago, actually about 6 months ago now I think, and I said I was going to make another video later and release the source code and explain in a little bit more detail about how to put it together if anybody else wants to give it a try. So that's what this video is going to be. Yeah, sorry it's taking so long. In fact, pretty much everything we see here, I actually had that ready back in April, and all I've been doing since then is just working on the software side of it every now and then, adding some new features and trying to maybe fix some bugs, and also writing some documentation and tidying everything up and putting it into GitHub. So this is the GitHub page here. I'll put a link to this in the video description and you can take a look at that. And I've done what I consider to be a pretty good job of explaining everything in this document in the main README here. So I'm just going to use this as my script, so to speak, for this video, and I'm just going to go through this for the most part and just look at what it says and show you a quick example of doing calibration for the sensors, and I also want to show you what I've set up for, you can submit your test results to the server and you can see other people's test results, although I'm not sure how far I'll take that. I might just stop working on that because there is, as you may know, there is this site called Mini-Quad Test Bench, and the guy who's running this, Ryan, this is really, really well done. So I'm thinking what I have is just really not worth pursuing when there's this much good data out here. It is kind of nice to sort of crowdsource something like this where you can get lots of people to do a little bit of work each and bring all those results together. But the trouble is, you've got to build one of these kind of contraptions, so there's quite a bit of outlay or effort to get started. And comparing what one person tested on their machine with what somebody else tested on another machine, you're not really getting a direct comparison by testing it on some slightly different machine, I think. So as far as comparisons go, it's much better to have one person with one test stand doing everything, doing all work. So I don't think I'm going to go through any further with my online sort of side of this test stand, but I'll see what people say about what it looks like so far. It's very, very rough what I have at the moment, but it's functional. And he's got really nice setups here for, you can interact with these graphs, choose a different motor and so on like that. So this is really, really awesome. Lots of detail too. So well done, Ryan, Harold. I really like this. This site is great. So anyway, back to this. So yeah, you'll need a 16 MHz Arduino, and I have made binaries for Linux 64-bit and Windows. I think the Windows one is 64-bit as well. I'm not going to make a Mac build, so don't ask for that. And the sensors that I have set up are a load cell, obviously, to measure the thrust. There is a current sensor and a voltage sensor. I'm using a Hall sensor for the current, and I'm using an analog to digital converter to measure the voltage, and that's using a voltage divider to bring it down from the battery voltage, which is, well, whatever it is, down to something that's within 0 to 5 volts for the ADC to work with. And I also have this little laser unit here which is shining through the propeller area onto the receiver at the bottom, and the propeller will swing through here and break the connection between that laser to measure the prop speed. So those are the sensors that I've set up, and I've explained them all here. Yeah, one problem I came across, I originally thought I was going to be making this video about 6 weeks ago, and I tidied up all my source code and everything, and then I thought, okay, that's good, everything's working on Linux, I'll just quickly switch over to Windows and port it to Windows because it's a Qt project, so it's quite easy to port. But no, God, I had endless problems. So to make a long story short, if you are running this on Windows, do not use an Arduino which has one of these CH340 or CH341 USB to serial chips. It's not going to work. You may be able to use Arduino programs, like upload sketches onto it and so on, but for whatever reason, the libserial port library that my program is using, it just does not play nicely with this CH340 USB to serial converter or adapter, or whatever they're called. But it does work just fine with, over there. It does work just fine with the official Arduinos, or the Arduino Uno at least, that have the 80 16U2. Is it? This is what's talking to the USB on the computer, isn't it, on this one? I think. And it should also work with a proper FTDI adapter as well, instead of one of those. So if you're having trouble on Windows, yeah, that could be the problem. And the trouble that you'll see is that the graph updating is all stuttery and slow, and you can't control it very well, and it's just horrible to use. Just the communication between the Arduino and the computer is not very good. On Linux, though, both of these work perfectly well. So I'm going to continue using this one on my particular test stand because this is the one that has these nice double rows of pins there that you can connect a male and female of each pin. It's very, very handy because you do need a lot of connections, and there's some other stuff broken out there which is quite nice. So the connections, I think I'll just skip through this pretty quick because I've actually described some of it already, but on the left is the component in question, and on the right is the Arduino. So I've listed up the connections like that for the ESC. Again, you have left is that component and right is the Arduino. and I've just written a little bit about each one of these components as well. This is the load cell amp, and I've had to do a little bit of fiddling with this, because when you buy these, they are set up to be 10 Hertz update rate, so 10 updates a second. It's not really that fast when you're trying to measure something like this, but they are also capable of 80 Hertz update rate. But you need to mess around with these two pins here. You have to detach this pin from the pad on the PCB, and you have to connect it to the one next to it. So what you're trying to do is you're trying to bring this pin to logic high by connecting it to VCC, which is there. And it's quite small and tricky, and you have to be rather careful to do it, but not impossible. So analog to digital converter, you'll need to make a voltage divider of some kind. Probably about 10 to 1 is fine. This one has quite a few connections, because I've used this as this analog to digital converter has two. Well, it has 4 actually. If you want to use all common grounds, you can actually have 4 ADCs running on this one module. But the way I've set it up is I've given them each their own ground. Probably not really necessary, but then that gives you 2 ADCs, and I've used those for one for voltage and one for current. So that's how it's set up there. You don't really need to look at that, because it's sort of described here what you need to do. Just thought I'd put this photo in here just in case it helps. And this is the hall sensor, which is down there with these connections. And you'll need to, I found it easier to take this little plastic thing with the screws on it, take it right off and solder directly onto the pad like that. So you need to break one of the power lines, either the negative or positive, I don't think it really matters. And you'll need to bridge that through this sensor to measure the current going through there. The one I have is up to 30 amps, which I think should be right for most of the stuff that I have to test, but you might want to get a higher current rating than this if you're going to test big motors. And then this laser TX thingy, that's pretty simple stuff. Highly recommend putting a buzzer on, because you can use that for feedback and warnings to let you know that it's about to start up. Speaking of which, there is potential for injury. There's no concept of arming or anything, so just be careful. Don't cut yourself. So I've listed up some basic usage here and some stuff, but this is what I'm going to go over now, and we'll have a quick look at this stuff. And right at the bottom here you can see where I've linked to the binaries for Linux and Windows. And a little bit about building there. I'm not really expecting anybody to try building it, but this is the Qt versions that I've used to build it, and it should build okay. I don't know. Let me know if it doesn't. Maybe we can figure out what the problem is. Alright, so enough of looking at text. So I have this set up here, and if I just start the program and click open to connect, I see my values coming in, and if I just push the motor there a little bit, so it's just put it all on screen. Now I'm not taking my own device here because the battery is connected, but what I'm doing is I'm just going to push it with something else. So you can see there that the thrust is being measured. So that's probably the most basic measurement you want to take, isn't it, the thrust? And I can do this to control motor speed manually. So I guess probably the first thing you'd do is to calibrate the sensors. So let's have a look at how you would do that. How small can I make this? Try putting this here. Okay, so calibrating sensors. We have voltage, current, and the thrust. So I'll do them in the opposite order, I think. Yeah. So I'm going to disconnect the battery, and I'll calibrate the thrust first, because this is the easiest one to demonstrate. So you need to measure the zero situation and also the situation where you're measuring a known quantity. So the known quantity I'm going to use is 100 gram weight, which is like that. And I think I'm repeating some of this from my first video, but bear in mind that some people might not have seen the first video, so it wouldn't hurt to repeat this a little bit. So with just the prop on the motor, I'll click measure 0, and if your thrust is not already showing 0 here, it should have to click this. Well, okay, it's not perfect, but it'll be close to 0. And then I'll put my 100 gram weight on and then click measure known weight. So I just have a little piece of fishing line here so that it's not too heavy. So when you're doing something like this, you kind of want to have the battery disconnected, right? Anyway, well, you can see I've calibrated this just before, so it's already showing me that measures at 100 grams, but it won't be the first time you do this. So at this point, you just click measure known weight. Nothing's going to change for me, but yeah, now lets it know that what it's measured, what it's feeling at the moment is 100 grams. Right, so remember to take that off. Very important. Okay, so to measure voltage, I will Firstly, with the battery still disconnected, so I haven't plugged it in there, you'll click measure 0 here. And again, it's not really changed much, but you should see a 0, pretty constant 0 reading for voltage now. And then you plug your battery in, and you measure the voltage of the battery. So when I plug the battery in, we'll see this orange line has come up to a higher value now, so it's sensing the voltage. And as before, I just calibrated this earlier, so it should be about 11.42. But just to double check, see what we get. So I'm just going to measure it from the balance port of the battery, which is over there. It's 11.42. Is that what it's called? Okay, so I'm just going to leave that there, but what you would do is 11.42 is what we measured as our known quantity, and then I'll put measure voltage there, so it's not going to change, but that's how you do it. Now, current is the same, so at this point we have 0 current, so I'm just going to click measure 0. So it's reading slightly non-zero value at the moment. Measure 0. It might actually be better to do this with the battery disconnected, I'm not sure. It won't make a whole lot of difference, so I'm just going to do it with the battery connected. And then, now this is a bit of a tricky part because we need to have a non-zero current going through the hall sensor, and to do that we need to have the motor spinning, and we also need to have a break in the power line. So the way I've been doing this is I got one of these XT60 pairs and I just connected them together, but only one wire is connected, so the red one is just separated there instead of folded on. And I put this in between there so that I can connect my multimeter clock here to measure the current. So let me just set that up. It'll take me a moment to get it done. Okay, so I have my current meter reading the current now, and if I spin the motor a bit, we'll see we are getting current reading. So now I can enter a known value of current and click measure current to measure it. But I need to set the current first. So what you need to do is set it to about a medium value like that, and enter that in. It's hard to get it exact because the value tends to go down slightly as it's running. So it's actually 0.433 when I click measure current. So it's not going to be exact, but let's see how close we got it by comparing what it says on there and what it says on there. That's close enough. So you could probably do a little bit better than that, but I think I'll leave it as is. So that's how you do calibration. Right, I guess the next thing to look at was defining a test. Yeah, let's look at that. So you define a test by entering rows of text into this little dialog here, and if it doesn't recognize the value that you've entered, like if it's just garbage, you'll see nothing underneath this past result section. If I just got that back how it was, you'll see that it's recognized those two lines as a beep of 1 second, and then we're going to set a constant RPM of 3,000 RPMs for 5 seconds. So this is what the automated test is going to do. Let's just take that one out, and I'll show you what this does when I do start test. I'll get to the parts in a minute. So all that does is beep for 1 second, and you can see in the text output here a little bit of info about what it recorded for that task. But actually nothing to record for that one. So let's do a S is for speed, and we'll do it for 3 seconds, and we'll make it 1300 microseconds pulse. So if you want to know where I'm getting this from, or if you want a reference for it, it's on near the bottom of the GitHub page. We've got some examples of how this is formatted and what other types of things you can do. Oops, so let me just... So this time we're going to run at 1300 microseconds for 3 seconds, and we should be able to see the clock spinning there when we do this. Pretty straightforward, I think. So yeah, you can just lift as many as you like of these. So I could do, make it a little bit shorter, 11, 12, 13. Yes, good. Alright, so you can see some text coming into this little text box here, and by the way, you can stop something, and if you want to look at the graph before it goes away, you can stop and start it with this button. and you can turn on which values you want to show on the graph there. And raw values is just the unsmoothed values that were the actual readings that were taken from the sensors. And some of them have quite a bit of smoothing, especially the RPM, because that's a very rough reading. But don't worry about that for now. So you can see here that last test that we had was a 1300 microsecond length pulse for 2 seconds. So it's showing what parts that was for and how many samples that were taken that were good samples. And a good sample is something that is within, I think, 5%. I'm not sure what I said, but I think it's within 5% of the target. The target in this case is a microsecond value, so we're never really going to be off that target because that's a direct value that we set. But if we were trying to do a constant thrust test or a constant RPM test, we can't actually set the RPM or the thrust directly. We have to sort of use a PID controller to adjust it, which means that not all of our samples are actually going to be within the thrust range that we tried to get to. So that's why this sample is counting how many were good samples. And this is just the values average for that